Hello everyone. Today I will present a study we have done in Shanghai Jiao Tong University, a graph-assisted autoplace update scheme for erasure-coded storage systems. Nowadays, Flash has been widely used in distributed storage systems. However, hardware failure and data loss are common in Flash storage, especially in MLC and TLC Flash, so high reliability is necessary. Replication is a traditional method provides high reliability, but its storage cost is high. Erasure coding is another typical method to ensure data reliability of storage systems with high storage cost. In the past 2 decades, numerous erasure codes have been proposed in storage systems. For example, RSKR can tolerate up to R failures. Data can be recovered from arbitrary K blocks. However, erasure-coded storage systems suffer from high update cost, as shown in the figure. In an RS32 erasure-coded system, an update of data 0 incurs 3 read and 3 write operations, while in the replication system, no read operations are needed. In the past 2 decades, several methods are proposed to improve the update performance. In-place update methods include party logging with reserved space, and speculative partial write scheme, but they bring extra IOs in updates. Out-of-place update methods include log stretch array, constraint dynamic stripping, but they ignore the information of files or objects, while may bring performance decrement. Some methods focus on network transmission optimization, such as T-update, Castle, CAU, and RACU, but they ignore the optimization of IOs. In party logging, once some data blocks are updated, the original data blocks are read and the deltas of data blocks are calculated and transferred to party nodes. However, it may bring both read amplification and write amplification. In log structure array, when data blocks are updated, the new blocks will be organized to new strips and written into disks. However, the LSA disturbs the distribution of blocks belonging to a file and need to design an efficient garbage collection strategy. To sum up, the existing update methods either cannot avoid extra I/O operations in update process or disturb the distribution of blocks which ignore the relationships between files and blocks. It motivates us to propose a novel method called GOOD to enhance the update performance. GOOD consists of 2 main processes, update and garbage connection. GOOD adopts auto-place update scheme to avoid extra I/O operations. Moreover, we introduce graph algorithms to minimize the performance degradation caused by possible destruction of the distribution of file blocks. GC is a necessary strategy to recycle disk space. Minimizing extra write operations and maintaining file distributions as much as possible are 2 main goals of GOOD. Therefore, in this process, graph algorithms are also introduced to match the blocks and the nodes. I will first illustrate the update process. In the beginning, some metadata is collected including parameters in erasure codes, mapping information, and file access patterns. To avoid extra I/O operations, GOOD transforms update operations into write operations. Once update operations happens, the updated data blocks will be stored in update buffer until the amount of buffered data blocks reaches a predetermined threshold. Meanwhile, the buffered data blocks will be flashed into disks in order to avoid that the number of these blocks cannot reach the threshold. To guarantee the fault tolerance, the updated data blocks must be combined to calculate the specific parity blocks and reorganize them to new stripes. When the stripes are reorganized successfully, they will be written into the storage nodes. The old data blocks will be marked as invalid and stored in the original places as usual. The valid and invalid data blocks are still stored in the OR strip to achieve the same capability of fault tolerance. The existing method Erasure also reorganizes the updated data blocks to new stripes to avoid extra I/O overhead, which is similar with good. However, Erasure only picks a path from one update block to one node in a random way. This may result in the data blocks belonging to the same file concentrating on a new specific node, which will significantly decrease the performance of file access. At the same time, if the updated blocks are written to different nodes, it will cause more complex metadata modifications. There are two rules in Good to determine which nodes the updated blocks can be written into. The first is no related first. It means the updated data blocks in the reorganized stripes are preferred to be written into those nodes in which the number of data blocks belonging to the same file won't exceed the largest one after the updated blocks written into them. The second is original node first. It means Good prioritizes putting updated blocks into their original nodes, which will reduce the metadata modification across nodes. The weighted bipartite graph matching algorithm is introduced to finding the appropriate nodes where updated blocks are written. I will explain it in detail later. The second part of Good is garbage collection. First, we define the invalid block ratio. Assume that there is a strip with k data blocks and I invalid data blocks. The IBR of S is I over k. When a garbage collection process starts, the strips with the largest IBR values will be recycled. Read, write, and update operations to the recycle strip will be blocked during the lock time. The valid blocks in the recycle strip will be cached to GC buffer. The GC buffer is organized as multiple queues. Each queue caches blocks of corresponding node. Blocks follow first in first out principle. The blocks in the head of each queue are the oldest block coming from those strips of which the number of valid blocks is small. The last part of garbage collection is to reorganize the strips with the blocks in the GC buffer and determine which nodes the blocks should be placed at. The key point is to minimize extra write operations and keep file distributions as much as possible. To address this problem, we introduce graph algorithms to match the GC blocks and nodes considering both cost of write operations and file distributions. Next, I will introduce the construction of graph in detail. As mentioned before, a weighted bipartite graph is used to find an optimal match between blocks and nodes in update and GC processes. In the bipartite graph, the vertices should be divided into two parts. One part consists of the updated blocks and another part consists of all the storage nodes in the system. The establishment of edges follows the principle. If the performance of file access doesn't decrease when DI is put at NI, the edge between DI and NI is established. The definition of width is the key part of the construction. Fi represents the hotness of file containing block I, which is defined as Fi minus Fmin over Fmax minus Fmin. Fi stands for frequency of file access. Mij represents the difficulty of metadata modification if blocks is transferred to node J. If block I is written into its original node, the Mij of corresponding H is set to 1 and otherwise it is set to 0. The weight of H between block I and node J is defined as 10 times Fi plus Mij. After graph construction, the optimal update or GC strategy can be obtained by solving the maximum weighted bipartite matching problem with KM algorithm or be modeled as a mean cost mass flow problem. To demonstrate the efficiency of good approach, we set up a cluster of 30 Docker containers. We used 4 traces to reflect real-world workloads. We also use 4 structures of Erasure codes. The traces and evaluation platform are shown in the table. We use 4 metrics including average response time, I/O operations, I/O throughput, and I/O load balancing in the experiment. We compare good with 3 typical update methods: RMW, RCW, priority logging, and log stretch area. Compared with RMW, RCW, PL, and LSA, good can reduce average response time by 55.33%, 49.01%, 24.23%. Compared with RMW, RCW, and PL, good can reduce I/O operations by 20.28%, 50.80%. Good can improve the throughput by 3.72 times, 2.99 points, 1.86 times. Good can reduce the variance of I/O operations by 30.20%, 27.88%, 31.26%. In conclusion, we propose Good to improve the update performance in Erasure coded storage systems. Good adopts autoplus update scheme and takes the parallelism of file access into consideration. The update and garbage connection processes are guided by the graph constructed in advance. The evaluation results demonstrate its superiority over existing approaches. That's all for my presentation. Thank you very much for your time.